The practical use and advanced estimate P of P capital P is substituted in this formula if N capital is large and first approximation is N naught equal to T square PQ over D square, which is equal to PQ over V. V equal to PQ over N naught, the desired variance of the sample proportion. In practice, we first calculate N naught if N naught over capital N is negligible, and N naught is a satisfactory approximation to the N of 4.1. If not, the appearance on comparison of 4.1 and 4.2 that N is obtained as N equal to N naught over 1 plus N naught minus 1 over N, which is equal to N naught over 1 plus N naught over capital N. Let's take an example. If the hypothetical plot groups example we had D equal to 0.205 and P small equal to 0.5 and alpha equal to 0.05 and T equal to 2, then the N value will equal to 4 times half over 0.0025, which is equal to 400. Let's assume that there are only 3,200 people on the island. The FPC is needed, and we find that N equal to 400 over 1 plus 399 over 3,200, which is equal to 356. This formula for N node holds also if the P and Q are expressed as percentages instead of proportions, since the product PQ increases as P moves towards to half or 50%. A conversion estimate of N is obtained by choosing P the value nearest to half in the range of which P equal is thought likely to lie. If P seems likely to lie between 5 and 9%, for instance, we assume that 9% for the estimation of N. Sometimes, practically, when estimating the total number N times P of units in class C, we wish to control the relative error R instead of the absolute error in P n times P. For example, we may wish to estimate NP with an error not exceeding 10%. That is, we want probability of absolute value of N times P minus NP over NP is greater than R, which is equal to the probability of the absolute value for P minus P is greater than R times P, equal to alpha. For this specification, we substitute Rp or Rp small for D in the formula 4.1 and 4.2. From 4.2 we get N node equal to T square PQ over R square P square, which is equal to T square over R square QP. Formula 4.3 unchanged. 4.6. The formula for N with continuous data. Most commonly, we wish to control the relative error R, the estimated population total or mean, with a simple random sample having mean y bar. We want that the probability of the absolute value y small bar minus y capital bar over capital Y bar is greater than R. The probability of n y bar minus n capital Y bar equal over n y bar is greater than R, so that the probability of the absolute value of y small bar minus capital Y bar is greater than R times y bar equal to alpha, where alpha is a small probability. We assume that y bar is normally distributed from the theorem 2.2. Clearly, 1 is standard error is sigma y bar is equal to n minus root n minus n small over n times s over root n. Hence, r times y bar is equal to t times sigma y bar small equal to t times n root n minus n over n times s root n. Solving for n gives n equal to n times s over r times y bar all square over 1 plus 1 over n times st over r y bar all square. Note that the population characteristic on which n depends is its coefficient of the variation s over y bar. This is often more stable and easier to guess in advance than S itself. At the first approximation, we take n node equal to Ts over r y bar all square equal to 1 over c times s over y bar all square. Substituting an advanced estimate of s over y bar, the quantity c is desired cv square of the sample estimate if n node over n is applicable. We compute n as in 4.3. n equal to n node over 1 plus n node over capital N. Instead of the relative error r, we wish to control the absolute error d. In y bar, we take n node equal to t square s square over d square, which is equal to s square over v, where v is desired variance of y bar. Let's take an example. In nurseries that produce young trees for sale, it's divisible okay, sorry for contraption. Let's take an example again. It's in a later late winter or early spring. We use that how many healthy young trees are likely to be on hand, since this determines the policy towards the cyclization and acceptance of order. A study of sampling methods for estimation of the total number of seeding was undertaken by Dawson, 1943. The data that follow were obtained from the bed silver maniple seeding 1 foot wide and 430 feet long. The sampling unit was 1 foot length and had bed so n capital equal to 430 by complete numerus of the bed was found y bar equal to 19 and s square equal to 85.6, these being true population values. With simple random sampling, how many units must be taken to estimate y bar within 10% apart from chance of 1 in 20? From 4.5 we obtain. So almost 20% of the bid has to be counted in order to attain the precision desired. The formulas for n given here apply only to simple random sampling in which the sample mean is used as the estimate of y bar. The appropriate formulas for other methods of sampling and estimation are presented with the discussion of these techniques. Estimation of y bar with given coefficient of variation is equal to root c. The results assume that y are normally distributed. If y square 1 s square 1 is the estimation of the variance from the first sample, we take the additional units to make the final sample size. So n equal to s1 squared over c times y bar square times 1 plus 8c plus s1 squared over n1 y power 1 squared plus 2 over n squared n1. The mean y power of a final sample is slightly biased. Take the y power hat equal to y power times 1 minus 2c. The estimation of y power with variance v take additional units to make the total sample size n equal to s1 squared over v times 1 plus 2 over n1. If S were known exactly, the required sample size would be S squared over V. The effect of the not knowing S is to increase the average size by the factor 1 plus 2 over n. This part was for sampling technique. Thank you for listening, and we will be again in another videos.